Right. So today I'd like to talk to you about. Oh well, I think I'd like to talk to you about a topic which is similar to what Theo has been telling us today. I will also be talking about model-independent ways of testing gravity. But the thing is that obviously, well, not so obviously, but like my scope will be much more reduced and it will stretch much less out than the book Theo has been telling us today about. And specifically, what I'd like to talk to you about today is I'd like to talk to you about why we would need to test gravity within the cosmological context in the first place. And I would also like to introduce some very specific ways of doing so. Specifically, I will be talking about a parameterization called the mu-sigma model, which you see here, and how we can use it to test gravity using CMB data. And I will be introducing a small problem that seems to be there in the 2018 data by Planck, which are CMB data, which seems to be, which is an alleged evidence for modified gravity, but that is an evidence that tends to disappear once we consider new data, PR4 data from the 2020 NPipe analysis. But I don't want to waste any more time, so I just want to get into it. So the importance of GR, general relativity in cosmology, is that it's basically one of the essential elements of what we call as this, what we refer to as the standard model of cosmology, which is what we use to describe why we see the universe to be expanding, why we see structures evolving in the way we see them to evolve. And apart from general relativity, as I'm sure all of you know, we have also some other very important ingredients that we add into our standard model, which are dark matter, an energy component that we add to explain, as we know, rotation curves of galaxies, but also at a cosmological level, we also need them to explain why the large-scale structure evolves in the way we see it to change in time. We also need dark energy, an important component to explain why the universe is expanding at all rather than contracting or being in a more stable form. And those are the two main components of the universe making up the standard model, aside from other components like baryonic matter, radiation, and things we're all used to. So, well, the standard model, the ΛCDM model, is a model that works actually very well in general. And but the thing is that with it we can explain a lot of things that we observe, like the cosmic macro background itself, and again the large-scale structure as we observe it. And it is quite astounding that we can use such a simple set of parameters to explain phenomena that are so widely different from each other. At the same time, there are problems with the model, and as you also all probably already know, one of the main problems that we're faced with is the tension on one of the parameters described in this model, which is this parameter here, h naught. This is the Hubble parameter, and at present, and it describes how quickly a universe is expanding at present. And the thing is that we measure it to take different values, where we consider late time probes, so like low redshift probes like supernovae, for example. And what we get is value that is somewhere around up here, where we see this green man trying to hold the additional value. We're at a value which is around something like 73 kilometers per second per megaparsec. While the thing is that if we use other probes at higher redshifts, like for example the cosmic macro background, which you see, which I'm also going to show you again, which you see here in the background, but which I'm also going to show you again very briefly, because the cosmic macro background is the main basis of the work that I will be telling you about. The thing is that with CMB, we tend to get a value that is actually right down here along this gray strip at the bottom of the figure. So as you see, there is quite some difference between early time and late time probes. And this is a difference that can be alleviated, as we see from this picture here, by modifying our model with early time physics and late time physics. And that can surely help us to alleviate the H-Node problem. But the Hubble tension is a problem that currently has not found a definitive solution. Another problem that is quite well known is a problem that deals with a parameter that doesn't describe, in this case, the rate of expansion of the universe, but rather the rate in which matter grows, with the way in which large-scale structure grows in time. And this is codified by this parameter here, S8. And the problem is still the same. If we're using in a very general idea, in a very general way, the problem is that when we use early time data, which are again, and the example of which I'm showing you again is our CMB data. CMB data are represented here by all these like blue lines. Basically, the measurements that we have for S8, which again represents growth of how matter grows in the universe in time. S8 is specifically present. We see that the value that we obtain with late time probes tend to be higher. Early time probes tends to be higher than late time probes, which are represented here by this orange contour here. Again, there are ways in which we can tweak our standard model to get an alleviation of this divergence between early and late time measurements. But then again, the S8 tension does not find a definitive answer. And actually, a way in general, and rather than introducing, for example, a different form of dark energy, as we can do for the H-Node tension, for the S8 tension, one way to get a solution for this divergence is to actually modify gravity. And the way to modify gravity is in a phenomenological and general way, obviously in the most general possible level, is by taking advantage of a parameterization actually taking advantage of the parameterization that I mentioned at the beginning of my talk. And this is just called the mu sigma parameterization. And to understand what it is, we just had to think of standard perturbation theory in cosmology. And here I think you can really see one of the differences with the treatment that I'm presenting to you now and what Theodore presented before. In this case, like we're not trying to make any connection to the astrophysical level, for example, and we're working at a purely cosmological level. So at very large, very linear scales. And specifically here, we are only modifying perturbations compared to the standard model of cosmology. We're not modifying anything about the background. We're now modifying, for example, the Friedmann equation, which in the post-Newtonian parameterization was modified through the, I believe if I remember well, the gamma parameter. But here again, we only want to concentrate on perturbation theory. And specifically, I wanted to look at equation 2 and 3, and even more specifically at equation 3, okay? The parameter that will be to most interest to us would be sigma naught, which is a parameter that we see here. And this is a parameter that is modifying equation 3, which is a sort of, which is a Poisson-like equation, which relates essentially, which tells us something about the evolution of this thing here, the sum of the two perturbation potentials that we use in standard perturbation theory in cosmology. And the sum of these two potentials takes the name of Weyl potential. And this is a quantity that tells us how light couples to gravity. And this coupling in this case is represented by the Newtonian gravitational constant here. And I think here we can make a distinction similar to what Theodore told us earlier as well, because like we can have G can take different meanings depending on the context that we see it into. In equation 2, G represents the coupling of matter to gravity. Because again, equation 2 only describes a variation of the potential psi. On the second case, for the Weyl potential, which is again the sum of the two perturbation potentials from the perturbation theory, in this case, G describes the coupling of light to gravity. And this would be of interest to us because, again, I will be talking to you about very soon about cosmological background, which is light, and which of course couples to matter, and the effects of this coupling are visible and measurable by the CMB. So again, this is also like probably a picture you also have already seen like plenty of times. There's nothing but the temperature map of the cosmological background measured by Planck back in 2018. And all these like intense red dots just represents like overdensities of all these blue and red dots are just representing the definition of temperature perturbation that you can see in equation 4. Very intensely red spots are going to be overdensity. Very intensely blue spots are just going to be underdensities. Now we can use this to make cosmology, but not exactly this, because like the thing is that our cosmological theory cannot tell us what delta T is going to look like at each point in space. However, what we can do, we can try to extract a statistical quantity. We can try to use instead a statistical property of the cosmological background. So, and the way this is done is by going from the map, which is like this picture that you see here, to the power spectrum of the cosmological background. Okay, power spectrum is in the end nothing but the variance of this perturbation given at different scales, different multiples, and the power spectrum looks essentially like the curve that you see in the smaller figure within a figure. Okay, at all like within the lambda CM model, this is what in general we expect to see. Okay, and this is what we measure with the cosmological background. What we expect to measure. The thing is that, as I said before, like we want to test gravity, and to do that, we want to see how gravity can change, how when we change gravity, we also change the way the cosmological background is going to be looking like. And the parameterization I introduced is the mu sigma parameterization. And interestingly enough, we can see that if we change this sigma parameter, which by the way within the standard theory, within general relativity should be equal to 0. Okay. If we set it to 0, then we recover the standard theory. However, we can also vary it, and the effect of this variation on the cosmological background can be seen here. Okay, we can see that the peaks are being smoothed out; they're getting flatter. So we're kind of losing power in this part of the spectrum, which is represented by this like red square here. But this power is then going to be redistributed at high multiples. So this power is not lost, but at the same time, it is just redistributed. But there is a change, okay, in the way the cosmological background changes when we change gravity. And in principle, if there is a modification of gravity, we should be able to see it, okay, within the cosmological background. So do we see it? The thing is that the data from Planck 2018 actually seem to see such a deviation from the standard theory. In fact, as we can see from the red contour here, we get an evidence for modified gravity, which is more. We get a deviation from standard gravity, which is more than the 95% level, which is quite an interesting measurement to be shown by Planck. But the thing is that this measurement is something that is only true within this data here, with PR3 data, the data that were released back in 2018 by Planck. And this evidence is not really confirmed by two other probes by other measurements made by using the cosmological background. And precisely, I want to point you at there are two measurements that are alternative to Planck, which are called ACT and SPT, which compared to Planck tend to measure higher multiples because they are ground-based. And because they are ground-based, we have this limitation that only allows us to measure higher multiples. And specifically, what they seem to be measuring about gravity is that is nothing but consistency with GR, with general relativity. Specifically, I want to point you at the this contour here, the posterior for sigma. All these measurements that use ACT as data set, they all agree with the value of sigma to be consistent with 1. Okay, and the same thing is true as well for SPT. So compared to the 2018 data from Planck, ACD and SPT, and but at the same time also weak lensing probes, they do not seem to show any similar evidence for modified gravity as Planck does. So this is a bit of a problem, not only because like modified gravity is not something that we expect, but also because there is this kind of inconsistency between cosmic and macro background measurements. So what we decided to do, and this is the I guess the core of work that I've been doing from an idea of William Geret, Aaron Barros in collaboration with my supervisor Eleonora Di Valentino. The idea was to try to see if this evidence for that Planck gave us was still there when we used new data by Planck. And the new data, the most recently released data by Planck are coded by PR4. And these are data that have been, this is data that have been obtained through the NPipe data pipeline. So these are new data analysis. At the same time, we also used alternative likelihoods to analyze this data. For example, this result was true by using for high multiple temperature and polarization data this likelihood here called PLIC. Now by switching data to new data, so going from PR3 to PR4 data, and going from PLIC to the helipop likelihood for high multiples in temperature and polarization, we see that this evidence is decreasing. Specifically for a helipop, the contour that we get is this green Shrek-looking contour that we see here, and we can see that this is perfectly consistent with the horizontal line, which represents sigma naught to be equals to 0, which represents just consistency with general relativity, right? So we have reestablished consistency with GR. Now, I just want you to remind you very quickly about the this equation this modified equation from the standard perturbation theory of cosmology. Specifically, like this equation, we also refer to as the lensing equation. And the reason is actually, I told you before, it's because this equation tells us about the evolution of the sum of these two potentials, which are the potentials that regulate how light reacts to gravity. And again, this the Newton's gravitational constant, as we see it here, represents the coupling of light to gravity. Thing is that since we're treating here again, we're talking about the main observable that we're dealing with here at the moment is cosmic macro background. Cosmic macro background is light, and light is gonna be impacted on by the intervening matter from recombination up to current times. And as an example, I want to show you this small picture here. So the idea is that on the top left corner, we see what the cosmic macro background could look like, or part of it is simulated to be looking like just after recombination. The thing is that then the light travels in time. It encounters structure, large-scale structure, and large-scale structure changes the way the cosmic macro background is going to be looking like because of lensing. Okay, and lensing is going to be regulated by equation 7, the lensing equation that we see here. And the end result is going to be something like the bottom left picture that we see here. Okay, so this is this is a result that we obtain by just like lensing, by just using a point function and lensing very specific point in our CMB map. In general, obviously the picture is going to be much more complicated, but you get the idea. Okay, the cosmic macro background is distorted, and this distortion by lensing, this distortion is something that we can use to make physics, to make cosmology. To give you a more quantitative idea of, well, a better idea, I guess, of what the lensing effect is on the cosmic macro background. I also want to go again from from the map, which is what we're seeing here, to the spectrum. Again, the spectrum is what we need to make physics, because the map is not something that we can really predict from theory point to point. So we need the spectrum to test our cosmological model, and specifically, like the effect of lensing on the cosmic background spectrum can be codified by another parameter. So previously, I've introduced the sigma parameter, which is a parameter that changes gravity, and when we change it, we are also changing the way the cosmic background spectrum looks like. And now I also want to introduce a second parameter, which is important to this analysis, which is the lensing parameter that we see here. Okay, and as you can see, by definition, within the standard model, we expect this lensing parameter to be just equal to 1. But we can also change it to see if there is some variation that we would not expect a priori to observe in the cosmic macro background. And if we increase the value of the lensing parameter, A of L, which means that we're increasing the amount of lensing of the cosmic macro background and of light in general, we see that again, we get a smoothing of the peaks of the cosmic macro background. Okay, so if the lensing is changing from what we expect within the standard model, then we should be able to observe this, okay, within the CMB. And by the way, I want to just let you know, I just want you to notice that as you probably remember from before, the effect of changing the lensing parameter A of L is actually very similar to changing the sigma parameter, if you remember from before, right? As you can see, this is just a plot that you just saw before.
Sorry, sorry, just keep track of time.
Yeah, of course, I'm almost done anyway. But as you can see, the effect of modifying gravity is again that of smoothing the peaks of the cosmic macro background. Same thing again for the lensing parameter. So as you can see, these two parameters are going to be correlated to each other. The effect of these two parameters is very similar, okay? And now the reason why I am stressing about this lensing parameter is because this lensing parameter is yet another parameter that presents a problematic measurement within the 2018 data by Planck. Again, as I said, we expect it to be equal to 1 within the standard theory. The thing is that in the 2018 data by Planck, which is the black contour that we see here, the black contour here, it is actually different from 1. Okay, it is at more than 2 standard deviations away from the value from value of unity. So as we can see, this parameter, the lensing parameter, just like the modified gravity parameter sigma, is at odds with seems to be at odds with general relativity. So to recap very quickly, as I just said, there are two parameters that have been measured by Planck to be different, to be divergent from their expected values within general relativity, within the ΛCDM model. And but the thing is that we have measured these deviations only within Planck 2018 data. So in this work, what we did was again trying to use new data, the new peer-for data from the N-pipe analysis by Planck with new likelihoods. I've already shown you what we got for just sigma, and I'm gonna show you as well what happens for the lensing parameter A of L. And what happens is that, and I guess probably it's not so surprising now, is that as we change our likelihood from click and then also to CountSpec, which is another, by the way, CountSpec is also another alternative temperature high multiple likelihood for Planck. And then as we land finally on Hillpop, our contours are like shifting to lower and lower values. And specifically we're getting lower and lower, as we see here in the green contour here. We're getting to values that are finally consistent with unity for the lensing parameter. And as we've seen before, they're consistent with 0 for the sigma parameter. So now we're consistent at the same time with both general relativity and the lensing anomaly that is a problem within Planck's data. Okay, and this is, by the way, on the right we can also see the equivalent result for an alternative parameterization of gravity, which is just codified by this parameter gamma that we can see here. its ΛCDM value is represented by this vertical line. But again, we just get consistency, okay, with general relativity. And but if you want to know more about this parameterization, I can tell you about it in a moment. So yeah, I think that's about it. That's about all I wanted to tell you today. And just as a final note, it is just interesting to show you that the anomaly that we saw in 2018 data can be shown to be mainly coming from temperature data rather than polarization data. But again, this is just a final note, and I don't want to take more of your time. So if you have any questions, I'll take them with pleasure, and thank you.
Thank you, Enrico. Thanks for the great talk. Any question?
Yeah, I have a question, but if other people want to go first, because we've already done a lot of talking, then they should.
Yep.
Okay, fine. I'll go for it. Yeah. Okay. So I wanted to ask about the about PR4,
Yeah.
and also a little bit about helipop. So, what kind of, because this is not stuff I really understand so well. What exactly is different about PR4 compared to PR3? Does it, for example, have like more data from like from high multiples, or say it's like the lensing, the lensing, the errors on the lensing potential smaller, So on the level of data, kind of what's different, and then also in terms of the difference between the Plick and the helipop likelihoods, is that about then again about the properties of the data and the underlying physics, or is it more to do with the modeling of say like systematics and foregrounds and whatever?
Yeah. Okay. Thank you for your question. So in general, I feel like it's a very complex issue, but so I tried to summarize it in. So you fell right into my trap. So here you go with the extra slide. So about the likelihoods, I guess yes, to an extent. One of the different. So what makes it different? So what gets you the difference between, for example, helipop and Plick is indeed some of the modeling that we use. For example, there are differences in how, I feel like foregrounds are modeled, and at the same time, compared to previous versions, we get a larger sky fraction. So in the end, we are actually using, I think, more data, and also we're using data taken at a larger multiple range. And that would be it that would be as far as I know for the likelihoods themselves. And as for the data, there have been also some changes from PR3 to PR4 indeed. And one of the things is that the maps show, again, the oval looking thing that I've been showing before, they're cleaner, which I feel like it means essentially that they've been able to identify foregrounds in a more efficient way and to eliminate them from the maps. That's one thing. And at the same time as well, they've been able to involve more data from higher frequencies. Okay, so in the end, so for the data, essentially we're using from PR3 to PR4, we're using more data and a different cleaning of the foregrounds, I guess.
Okay, so it could be a little bit of either possible explanation. I guess it's kind of hard to disentangle.
Yeah.
Okay, no, that's cool.
So
yeah, and thanks for the very, very nicely done talk as well. It's what I should have said at the start. But yeah, thanks.
Thank you. Thank you very much.
Thank you all for attending this session, and I hope to see you all in the new year.